A four-stage Saturn V rocket was used to place the Apollo spacecraft into a parking orbit around the Earth. The first stage shot the rocket up about 42 road miles, and the second stage carried the rocket even closer to orbit. The third stage, called the S4B, contained the combined command and service modules and the lunar module. After a couple of orbits, the third stage rocket fired to place the spacecraft into a trans-lunar trajectory. Shortly afterwards, the crew in the command module performed a maneuver to pull the lunar module free of the S4B. Both the S4B and command and lunar modules continued on a trajectory to the moon, the used third stage rocket being discarded by directing it into an orbit around the sun or by crashing it into the lunar surface. Having established lunar orbit, 2 of the 3-man crew entered the lunar module before separating from the command module. After a few orbits, the lunar module descended to the lunar surface. 2 or 3 days later, the ascent stage of the lunar module blasted away from the descent stage to rendezvous with the command module that remained in orbit. Once the crew had been reunited, the lunar module separated from the command module and was sent on its way. The command module entered a trans-Earth trajectory, and on reaching Earth, the command module separated from the service module, entering into an orbit before splashdown in the ocean. Exceptions to this profile were Apollo 8, which had no lunar module, and Apollo 10, which never landed on the moon. Considering what the Soviets had demonstrated was possible with unmanned spacecraft by the end of 1970, which is when Luna 16 returned a sample of moon rock, the astronauts in the Apollo missions were surplus to requirements. And apart from launching a craft from the lunar surface, which they had never achieved prior to Apollo 11, the only maneuver NASA had never attempted under remote control was docking the command module with the lunar module, which was required during extraction from the S4B stage of the Saturn rocket and following lunar ascent. Whether or not this procedure could be automated is irrelevant in the context of the mission. It was only necessary in order to transfer the passengers from one module to another. The truth is, for NASA to even consider sending humans to the moon at this point was reckless beyond measure on many levels.
The skin of the limb in some places is only as thick as a couple of layers of tin foil, and that's all that protects us from the vacuum of space.
We can get away with this because...
Manned or not, there can be no doubt that NASA sent 9 Apollo spacecraft to the moon. Unlike the USSR, whose space program evolved behind the secrecy of the Iron Curtain, the USA had to be seen to be transparent even if they weren't. How much more transparent can you be than televising the entire event? But all spacecraft need to communicate with the Earth, especially those under remote control, and you can guarantee there were always plenty of ears tuning in on both sides of the political divide. NASA's ears for the Apollo program included the Manned Spaceflight Network and Deep Space Network, with stations in California, Canberra and Madrid, each equipped with 1 or more dishes from 85 to 200 feet in width. Such huge antennas and ultra-sensitive receivers were essential to cope with the very weak signals generated from a spacecraft hundreds of thousands of miles away.
Frank, could we go to 2142 minus 75, please?
Okay.
And that was the astronomer telling our telescope driver to move the telescope to the next source in the sky that he wishes to observe.
But as John Sarkisian, an operations scientist at the Parkes Observatory in Canberra, explained, keeping track of a spacecraft travelling at thousands of feet per second and so far away was not easy. The tracking data provided by NASA was in the form of a list with the predicted positions of Apollo 11 given in 4-minute intervals. The telescope operator, known as the driver, would point the dish at the first predicted position. He would then move the dish in both axes at the correct rates so that 4 minutes later, the dish would arrive at the next predicted position on the list. Often, however, if the dish wasn't on position at the assigned time, the driver would have to move the dish quickly in order to catch up. In the early missions, tracking data from Houston was often hopelessly inaccurate, and location of the spacecraft required an inspired guess plus a square search. In the later missions, the predictions improved, which was especially fortunate for Apollo 13. Halfway around the globe, at the enormous 250-foot Jodrell Bank Observatory in England, a group of scientists were eavesdropping on the Apollo conversation. They were officially tracking Luna 15, an unmanned Russian space probe in orbit around the Moon, when the giant Lovell radio telescope tuned into communications with Apollo 11. Engineer Bob Pritchard, monitoring transmissions, explains how they could hear every word. You had the voices of the astronauts as they talked to ground control, and they retransmitted the voices of ground control talking to the astronauts, so we could hear both sides of the conversation. Of course, Pritchard only assumed the conversation to be between the astronauts aboard the distant spacecraft and ground control on Earth, when in fact they could all be sat in the same room as long as the illusion of being hundreds of thousands of miles apart was maintained through the familiar beep and delay we have come to associate with deep space communications.
Okay, Bob, I owe you a bias reading. Okay, or you can get it later. There's no hurry on that. And we're off to the LSEP. Yeah, I'm going to give it to you right now. Okay, ready to copy. I presume you have a UHT out at the LSEP, Jack.
But wait, if what we hear on live TV is both sides of the conversation as it is transmitted from the spacecraft, there shouldn't be any delay between Capcom's questions and the astronauts' replies. And there should be a much longer delay when the astronauts say something, because it takes time for Capcom to receive it, and the same amount of time for their response to reach the spacecraft.
Okay, Bob, I owe you a bias reading. Okay, or you can get it later. There's no hurry on that. And we're off to the LSEP. Yeah, I'm going to give it to you right now. Okay, ready to copy. I presume you have a UHT out at the LSEP, Jack.
You'll have to wait until a later video for the answer, and it's probably not what you were thinking. For once at least, and possibly the only time, we have third-party confirmation that NASA sent something to the Moon that was capable of receiving and retransmitting communications from Earth. The question is what? Because it wasn't the command module. All most of the world knew then, and knows today, is what most of the world has been told by NASA according to the mission profile, corroborated by TV broadcasts, movies, audio files and photos, all of which was under the control of NASA, and none of which proved the Apollo crew went beyond the safety of a low Earth orbit.
We don't even know how to rendezvous in Earth orbit yet. No. How are we going to be able to assure ourselves that we could get the two vehicles together